Hi, so I'm here to talk about real-time risk management using Kafka, Python, and Spark streaming. I work at Shopify. I'm a data scientist or data engineer or whatever my title is, not really sure. My name's Nick. So I'm from Canada, and I'm very Canadian, and I'll try not to say A, but I do really like hockey, so I have a couple references in here. I hope that's okay with everyone. Yeah, so Shopify is a commerce platform where, say, if you make like a cool backpack or something and you want to put it online, you can go online, shopify.com, create a store, sign up pretty quickly, take a picture of your product, upload it. Within like probably an hour, you can be accepting credit card transactions, and with that credit card transactions, here comes risk. So yeah, underwriting credit card transactions is risky because there's a potential for a loss if a stolen credit card is used to make a purchase and the bank recovers money from us. So like say if your credit card's used fraudulently, you call your bank, what the heck's going on? I didn't do this charge. They get the money back from us. If the merchant doesn't have enough money in their bank account, then we end up having to foot the bill. It's also possible that they might sign up for a store and then process stolen credit card transactions in an attempt to get us to send money. They might also create like a fake product that they never intend to ship, like say like, oh, pre-orders for this product that's going to ship in October, and they just never send it, and they're gone with their money by the time we get chargebacks. So we need to check credit card transactions and stop these bad actors from stealing money from us. The problem is that the vast majority of these transactions are actually legitimate, which is a good thing, and we have a ton of transactions. We don't want to punish our real merchants by holding back money that we don't need to, just because there are some bad people, so we need to be really quick at this. They need to keep their cash flow running to keep their business, to buy more products, to pay for marketing, and holding back money from them is just a bad thing. So we also need to avoid losing money. We could lose hundreds of thousands of dollars a month, probably more if we were to just ignore the problem. We need to be sure that our risk analysts are spending their precious time looking at the right shops and the right credit card transactions. The thing about risk management too is you don't have to be the best at it, you just have to not be the worst, because all the fraudsters will figure out who's the worst at risk management and risk analysis, and they'll just target them because they're the easy people. So here's some numbers about Shopify. We've processed $12 billion in GMV or transactions. That's US dollars, I believe. We have over 200,000 merchants. Some big names like Tesla Motors, Wikipedia, and GitHub. Bunch of others too. This is actually outdated. I forgot to update this yesterday. It's probably about double that now, 14,000 events per second coming from our application. These are not including like Nginx logs or anything like that too. Like this is just straight event, like Kafka events that are coming out of the application. And we have 7 risk analysts right now. I think actually that number might be 8 too. And that's a lot of events per second to look at, like for 7 people to look at. So we need to somehow filter that down. So here's the first hockey reference. Being a risk analyst is kind of like being a goalie. Goalies are good at saving pucks, but they can get overwhelmed if you fire too many of them in quick succession. There's a lot of padding. There's very little space. So my friend Alex, he's the goalie for my hockey team. We're very bad. Not his fault. So we need something to filter out these high volume event streams that the Shopify application produces so that our risk analysts aren't overwhelmed. We also need to make sure that we're not sending them too many non-risky events, and that we are sending them the actual risky events. Like we don't want to miss any actual risky events. We want to reduce their workload while still ensuring that the true risky events don't go unnoticed. So we need defenders, like this guy here. He's smiling, he's patting the goalie on the back. He probably shouldn't be smiling, because if he's patting the goalie on the back, he's like, good job, I didn't do my job, and you did yours. So we need some defense that can block the shots and help the goalie out. So we built a stream processor that can filter down these high volume event streams. And then we do an HTTPS post for each risky event, and we send it out to a custom-built case management software that our risk analysts look through. They'll look through these queues and decide whether the events are risky. They can see all events for a shop under a specific page. Then they can take appropriate action, which might be like email the merchant and say, hey, what's going on? This seems kind of sketchy. Or they might shut down payments for that, or send them off to another payments processor. The application's called Pat Down, which is kind of a joke for the airport security line. You know, you go through the metal detector, and if you get set off, then you get a pat down. So who's familiar with these technologies? I'm assuming Spark Streaming, everyone here is pretty familiar with. How about Kafka? Can I see hands? Okay, so pretty much everyone. And Zookeeper, hands? Less, but still a lot of people. Okay, so yeah, I gave this talk a similar talk at PyData before, so not everyone was familiar with Spark Streaming, so I figured I'd probably just skip over the slide here, or at least just do a very quick skim. So Kafka is a fault-tolerant and distributed publish-subscribe message buffer originally written at LinkedIn. You can define a list of topics and produce messages to those topics and consume those messages elsewhere. They're very cheap to produce too, like in terms of time. If you create a Kafka event, we have this underlying queue that goes into, I think it's like the POSIX sysv message queue, and then we read from it later and actually emit those to Kafka. So it's very fast. We want to log these events super quickly from Shopify applications. We don't have to do a slow database call. And then be able to read those events from any other application that has access to Kafka, say an automated email or dashboard or Spark Streaming. It has ridiculously high throughput due to some engineering decisions. Can I get the notes scrolled down? That's good. It has a retention policy, so we only store messages for about 7 days, for most of our topics at least. That means if there's events that we're interested from 10 days ago, we need to do something else, like call it to a database or something. It has an at least once guarantee, meaning that some consumers of the events might hear the same message twice. These topics are broken up into partitions, as you can see here. And event ordering is only guaranteed within a partition. To ensure all data for a shop is received in order, we key the shop to the partition. So, shop 300 might go to partition 1, and it'll always go to partition 1, so we can always receive that in order. And if it slows down, you just add some more computers to your cluster. So Zookeeper is a distributed data store that stores data in tree formats. We use it as a way of storing our configuration details for Spark Streaming. I believe the base implementation of Spark Streaming using the receivers, which I'll get to later, that also handles Zookeeper storage for you. Just out of the box. We have to do some custom stuff just because we use it in a different way. It stores the index of the last message, the last Kafka message it heard. So if the streaming job shut down or killed or the machine's unplugged, it can restart from where it left off. And then Spark Streaming. So Spark Streaming is just these discretized RDDs, like so 30-second batches or half-second batches of RDDs, and you can define operations on them, which are just pretty much standard Spark operations like map, filter, reduce, all those kinds of things. And it handles splitting up the data across the cluster so you can get faster parallel processing. It's written in Scala, just like I believe all of Spark, but it has a very good Python API, and we use PySpark at Shopify. Just because it's harder to find Scala developers, and the Python's fast enough for our uses. Can I just scroll the notes down? I think there's no more, but I just want to make sure. Okay, so as I was saying, the old way, or I guess standard way for Spark Streaming to be used is what's called receivers. So Spark Streaming's original interface to Kafka was through a thing called a receiver, which loads chunks of data and then stores it into a queue in memory to be processed later. So like every, whatever your batch interval is, ours is 30 seconds. Every 30 seconds, you take a chunk of data, you create an RDD, and then eventually that'll get processed. Probably within 30 seconds, if that's your batch size, because otherwise you're going to fall behind. This is a slight simplification, but it should give you the general idea of how it works. So yeah, you receive events from Kafka. At T1, you build an RDD from these events. Then you process it. While some more events are coming in, build another RDD, process it, while more events are coming in. Kind of simple. So receivers were designed to work with all data sources and not just buffered sources like Kafka, which means that you have to make them a lot more general, and that means they're less powerful for when you do have things like, you can ask from a specific offset and replay from there. So there's a couple problems with receivers that we ran into at least. The first one is the only way to get at least once delivery, it makes it hard to deploy new code. So there's a thing called checkpointing and the write-ahead logs, which means every time you receive this data off of Kafka, you write it down to HDFS and basically keep it there until you're done processing it. But it's not just the data, it also takes the entire DAG and writes that down to disk. So if your job fails, you load the checkpoint on startup, but it'll also load the DAG, which means that you can never deploy new code because your instructions are already saved there. So what you have to do is come up with something like different. You have to do something different to actually deploy new code. So for the other problem is Zookeeper has updated which offsets to start from when the data is received, not when it's processed. So as I was saying, you receive these 30-second batch intervals, and each time you receive them, it'll tell Zookeeper, yeah, I've processed up to here. So what happens if you're only, or sorry, received up to here? So what happens if you only like kind of process the data up to here and then your job dies? You're going to start from here and miss some data, which is when you have to use checkpointing. It also makes traditional Kafka monitoring tools less useful because your job could be, like how they work is you get the current offset from Kafka, the current available offset from Kafka, and then subtract the offset you've processed up into, and you can see like a latency in terms of offset numbers. When you're doing this, the job can be chugging along happily, processing data, and Kafka monitoring is like, yeah, everything's good, and then your job dies, and all of a sudden you're really far behind, and you don't even know this. The final problem is it's kind of duplicating work because we're already doing a lot of this on Kafka, and the receiver also buffers the data. So it's back down. So they're duplicating the work of Kafka and adding complexity for no real gain. So we use the receiverless, or I believe it's called the direct method is another name for it, which is awesome and we love it. So the receiverless approach was designed with data sources like Kafka in mind. You have to handle all the offset management in Zookeeper yourself, but you get a lot of power with this. So you tell Zookeeper after you've actually processed the data. So if there's a problem between when you get the data and you've outputted it, you won't actually get data loss. The downside is you have to do a lot more work when it comes to Zookeeper management. Hopefully this will mature, but I believe the core developers for now are reluctant to add an offset management API to Spark Streaming as things are changing, and it seems like Zookeeper is falling out of favor with the Kafka community, and they're going to be doing something else different in the future. So I think the Spark devs are waiting for that. Can I hit the notes scroll down? So another downside is that the Python API and documentation often falls behind the Scala documentation. So this isn't actually really too much of a problem because you can just look at the Python code and see what's available. But the thing is, if you're reading a documentation and it says, hey, this isn't possible, it actually might be possible. You just have to look at the code to see whether it is. And then, yeah, sometimes the API falls behind. So like I've had a couple commits to Spark where I just basically copied the API to Scala and put it in Python so you could do the exact same stuff. The other thing is it's kind of very experimental. So how it works is you have events, and then the Spark engine processes those events, and then you get more events, and then it processes the next set of events. And after you process the events, like after you finish processing that RDD from T0 to T1, then you tell Zookeeper, hey, I've done this. So that has a lot of benefits because then you can get at least once delivery. You can deploy new code because you don't need checkpointing, and you also get the nice monitoring. So as I just said, checkpointing is not needed to get an at least once guarantee. Here's the general structure of how our jobs work. We load the Kafka offset from Zookeeper where we left off. If we did not have, like if it's the first time a job's run or if we've reset its progress, it will start from basically the earliest available offset and process all that data. Then we tell Spark Streaming to create a D stream that consumes from Kafka, starting at the specified offsets. I think it's Kafka utils.create direct stream in Python land, and then you pass it the topic or the offset and all that information. Then you define your processing step, like filter out the non-risky events. Define your output step, like post the data to a case management software or send an email or something. Then you save the Kafka offset to the most recently processed event to Zookeeper, and then you start your streaming application and grab some popcorn and watch it. The thing is about streaming is you can't actually change the DAG after you've already started the application, so you just basically define all of the steps, and then you dstream.start, or Spark context, streaming context.start, and it will start working away. So here's the example that I like to go over, risky products. So a lot of these things are considered risky, at least for us. Hair extensions, I'm not sure why, but they're basically just always fraud. If you don't know what they are, they're things that you attach to your hair to make your hair look longer. Some other things are cannabis, because we're not allowed to process that through Shopify payments. which is our credit card processor. Vaporizers, that's another thing. Travel package, I don't believe we're allowed to sell like travel packages, or I don't think, at least not on Shopify Payments. You can on Shopify, but not on Shopify Payments itself. And then a couple others. So how it works is we get this RDD with all these fun products. Taylor Swift t-shirt. I have kind of an unhealthy obsession with Taylor Swift and hockey. So we take that RDD, we filter it, which just uses like a kind of a simple filter that checks if the regex for the risky product title is in that product title or description. And then we create a JSON blob out of it that just kind of is what the application expects. And then we do an HTTPS post out to that case management software. So it's pretty simple. It ends up looking something like this. This is obviously a simplification. All these functions are elsewhere. But this is the general format of most of our streaming jobs. They're quite simple and nice. And then we have some work built around it that takes that data and posts it out to pat down. So one of the problems that we ran into was time-windowed aggregations. They're not quite ready for prime time yet. The reason for that is because the windowing, actually I guess I should explain what the time-windowed aggregations are. You might want to sum the value of orders for the last hour for a specific shop and then see if it goes over a certain amount, maybe for new shops. If they have a high number of orders in an hour, or if they have a high number of risky orders in an hour, that's also a bad thing. So the problem with this is it's based on the received time of the event, not the time the event was created. So say, for example, if you've fallen behind and you're 7 days behind on your processing, and then you process all of that 7 days in 30 seconds, that would all fit in the window because it's the time the event was received, not the time the event was created. But we do have this event timestamp on each of our Kafka events, so we can actually kind of do stuff like this. It also requires checkpointing to be enabled, which, as discussed earlier, kind of has its own limitations. We did implement our own version of time-windowed aggregations for streaming jobs, but it ended up being like quite complex, and we're also not sure if it really worked. It seemed like it was working, but we weren't 100% sure. If you're interested about that, I was going to talk about it here, but it's kind of like probably an entire presentation on its own, so just come find me after if you're interested. And the last point is the core developers of Spark Streaming have said they actually plan on addressing some of these shortcomings in the next couple of versions. I was talking to TD, and he was saying that he's working on a new framework for stream processing. I believe it was talked about this morning, or maybe tomorrow morning. And that should make these kinds of things a little bit easier, but it's actually a very complicated, hard problem to solve. So kudos to them for working on it. Means I don't have to. So the future of Spark Streaming, at least for us, time-windowed aggregations, as I said, it's a necessity for most non-trivial jobs. What we ended up doing is we actually ended up just using batch jobs that loaded in the data required, did the aggregations, and then sent that out to pat down on its own, which is not ideal because we would like to have them in as real time as possible, but it works for now. So performance streaks, we haven't really spent any time on this. There's a lot of potential for gains. I don't know if our data is kind of low volume compared to some people's, but it just seemed to work really well. We had a couple jobs where they were like getting close to the 30 seconds, so we did some, we added a repartition here and something else there and changed some of the Spark options, and it seemed to just work fine. Yeah, so there's probably a lot of room for work on this. The cool one that everyone always talks about is machine learning. So since we actually put these into a case management software, and the risk analysts look at them, they say this is good, or like this is bad, and I needed to do something about this. So with that information, we could build a machine learning model, because that's very binary data. And then we could probably use that machine learning model to filter these events more smartly, because maybe the way we're doing it right now isn't the best way. So improved monitoring. We're only monitoring the basics right now. We're only monitoring like offset lag. What we would like to do is get time-based monitoring, like how far behind is each partition in terms of event time. That's kind of tricky to do just because of Kafka limitations. It's hard to ask for like what time an event was created at. I believe in the new version there might be an API for that, but I think it's also approximate, which is like might be good enough, but we don't know yet. So I put this in the future, but I actually forgot. We have been using Cassandra in some of our jobs. We also use broadcast variables, which are awesome for performance. So if for a risky products example, we have whitelisted shops, and we don't actually care about them. I guess they're blacklisted because they've actually been kicked off the kicked off the platform for credit card transactions, and we don't actually need to look at them anymore. So we can blacklist them. You can also use Cassandra for something like that. Usually if it's a lot bigger than a broadcast variable can be. Broadcast variables, I think, can't be too big just because they all go out to all of the workers and they might run out of memory on that machine. So an improved receiverless API, as I talked about earlier, would be nice, but I'm not sure if it's coming anytime soon just because of the changes to Kafka. So I actually kind of burned through this. I got through a lot quicker than I expected. I did it before, and it took half an hour without questions. Yeah, just some of the slides had icons. I have to give credit for that just because of the license. It's an awesome project, Noun project. Check it out if you're making your own slides. We're hiring. If you're interested in any of this stuff, or pretty much anything else data science, you can go to shopify.com/careers. I believe the posting's called Business Intelligence Developer. We're experimenting with our titles just to try and find the right candidates, but pretty much anyone in this room would be good for that. We also have data engineering position too, which is more DevOpsy than the standard data engineering positions. So thank you. That's my Twitter handle if you want to follow me. I don't really tweet that much, so probably not that interesting. Any questions? Yeah, so can I give a brief talk about the time-windowed aggregations? So how we ended up doing it, and it's super complicated, so it's not a fun thing to explain without slides. What we ended up doing was each time events would come in, for each shop, we would calculate the minimum timestamp, or a time block, I guess, because we put them into blocks. We calculate the minimum time block for that batch. Then we would, next, we had to do this kind of janky thing where we were memorizing the offsets for 60 minutes ago and only committing them after we went past the 1 hour of burn-in, or no, sorry, only committing them after each batch processed, and then we had to burn in the first hour of data and then not emit until after that. As you can see, it's pretty complicated. That's why we didn't end up doing it. We ended up just going with the batch API instead. I'd say come. I can show you some code after if you want to see. Any other questions? Yeah. So how do we do integration testing with Python? And unit testing? Okay, so actually that's a very good question. I was saying this talk probably could have been a bunch of different talks. We actually wrote our own kind of mock RDD and mock dstream. The mock RDD is probably where the most of the code lies, and it's just using Python's filters and maps and stuff. The mock dstream is really tiny. It inherits from the actual dstream and uses most of the code of the dstream with just a couple things that don't actually call it Java, and kind of give us a fixture there. As for integration testing, we don't really do too much of that except for the basics. We just want to make sure that everything kind of works, and then we just assume that our mock RDD, mock dstream is good enough and it will work, and it has been so far. Yeah, all of this is from the Python land. We just want to kind of keep the tests run quickly. We want to keep a fast deployment cycle, and we haven't run into any problems yet. We actually, on our continuous integration, we actually ran using the real dstream and RDD for a while, but then once it worked fine between our developer machines and our circular continuous integration for quite a while, we just swapped over CI to use the mock ones too. Mocking on Scala versus benchmarking. We haven't done any just because, again, our data team used Python before, and that was what we were most comfortable with. So I have seen some performance benchmarks online, and it seems like Scala is fairly a lot faster than PySpark, but I did see some also newer ones with the data frames API, and I've seen that data frames can actually keep up with the Scala, if not outperform it, I think, even from Python land. Can you say that again, sorry? Java, Python, and Scala. Yeah, so the Scala API is going to be the most up-to-date. I believe the Java API will be the same just because you can actually just import those classes because it's all JVM. And then the Python API is like pretty good, and it's pretty trivial to add new features if they're not there, if they're not at parity with the Scala API. So the question was, can you mix and match? And I think the answer is yes. We only use Python. We did try and replace some of our more lower level code with some Scala and Java, but it ended up actually not adding much improvements just because of the serialization, which is what takes up most of the time anyways. And on serialization, that's another thing with writing these streaming jobs. It seems like sometimes the serialization isn't quite there, and you might get pickling errors, but that's mostly just because you're passing around objects that don't know how to be serialized properly, and that's pretty easy to fix just by not passing them around. Which serialization format do we use? We just use, so on HDFS we use, and Kafka we use JSON. Yeah, it's all JSON. I think we're trying out Parquet, but that's not in production yet. Questions? Yeah.
For doing the time window aggregation, did you consider writing the events into a data store and then querying the data store?
So for the time window aggregation, the question was, have we considered writing events to a data store and then querying the data store for time window aggregation? And the answer is yeah, but we didn't want to complicate the stack too much. We do use Cassandra, and we were going to be using that for the time window aggregations as well. But at the time I was writing them originally, or the time we were writing them originally, it wasn't production. Like our instance of it wasn't production ready yet, so we didn't end up using it. We just ended up going with the batch jobs, which were simpler anyways. In the back, I think he had his hand up first. How do we handle code changes? Yeah, so the question is how do we handle code changes because there might be a downtime for the streaming job? Yeah, every time we deploy our code base for all of our Spark jobs, we actually have the streaming jobs detect when the git SHA that it's running is different from the actual current git SHA and master. We write that git SHA down to HDFS every deploy and then read it up like every 30 seconds, and we use the await termination or timeout function, I believe it's called, in Spark. So yeah, we do have downtime, and it happens relatively often, but for most of our applications that doesn't matter too much. We just have our streaming applications scheduled to start every 5 minutes unless they're already started. So mostly that downtime is about 5 minutes. Again, we're not serving web requests or anything here, so that's not a huge concern to us. We do have another data team that actually does the internal dashboards in Shopify stores, and downtime is more important for them because when orders happen, if you look at the orders page and you see an order but it's not in your order count, you're kind of like, what's going on? Like this is not cool. And then 5 minutes later it appears, that's kind of a bad experience. So I believe what they're going to do is try and have the jobs probably start more often, so that delay is less noticeable, but that's not a very good answer. That's something, yeah, we didn't really care about that too much, so we didn't actually have to work on it too much. Yeah, that's one thing I forgot to talk about. So the question was, if we go down and we save the offsets after processing, there can be duplicated, and that's kind of the at most or at least once guarantee. You're talking about getting an exactly once guarantee, right? So that's not something, like we engineered our output system, this pat-down program, to actually be idempotent, which is kind of hard to do with windowed aggregations, but for standard, like, have I heard this event yet? Okay, yes, I can ignore it. It's just like a MySQL or Postgres, I forget, like a column that just has a unique check on it, and that's how we handle duplicated events. I think we're pretty close to done. Probably one more very quick question. Yeah?
You mentioned this direct access technique. So it's implemented by, it's not standard for Spark.
It's in the actual Spark, in the Spark repo. It is there. It's just kind of, it's experimental. It's not the main one. But I was talking to TD yesterday, and he was saying that they're designing I believe, a new system that's kind of based off of that one, that is actually built with data sets like Kafka in mind, where it can actually know, what events happened when, like which it heard last. And it's actually part of Spark streaming, yeah. Yeah. Okay, I think that's it. Thanks.